This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on continuous compound interest together with exponential growth and decay. For continuous compound interest, our formula is A equals PE to the RT. E is a number approximately 2.718. Let's define all the other variables. A is a total amount of money in the account. P is the principal, that is what you initially invest. R is the annual interest rate, and T is the amount of time in years that the money is invested. So we assume this is compounded continuously. So this is the formula to go ahead and find the amount of money on account if it is compounded continuously. Now, it's not realistic to invest money in an account that compounds continuously, but things like the inflation rate are perceived to be compounded continuously. And for something that's compounded daily, compounded continuously, and compounded daily are pretty close anyway. So this is a nice model for us to look at. Here we have $5,000 is invested in an account paying 2% annually, compounded continuously. How much is in the account after 7 years? How much is in the account? We're looking for A. 5,000 is what's invested. That's P. 2% is our rate. We'll make that 0.02 for R. 7 years is the number of time. T will be 7 years. So we define all of our variables of interest, and our formula is A. The amount on account is PE to the RT. So we'll plug those values in. 5,000 for P, E, again 2.718 thereabouts, to the R, 0.02 times 7. And then throw that into a calculator and you get an answer of 5,751 and 37. So at the end of 7 years you would have $5,751.37 in the account. Okay, our next question requires us to find the time. So again, 5,000 is invested in an account paying 2% annually, compounded continuously. How much time must pass before there is 8,000 in the account? So we have 5,000. Interest rate is 2%, 0.02. The amount on account I would want to be 8,000. So this time I have to solve for T. So plugging in those values, A is 8,000, P is 5,000, E to the R, 0.02 times T. We'll do some algebra to go ahead and solve for that T. Dividing both sides by 5,000, 8,000 divided by 5,000 is 8/5 or 1.6. So we get 1.6 is e to the 0.02t. We pull the exponent down by taking a natural logarithm on both sides. So natural log of 1.6 is natural log e to the 0.02t. And then we can pull the exponent down and make that 0.02t natural log e. But the natural log e is just 1. E to what power is e? E to the first is e. Natural log e is 1. So we get log 1.6 is 0.02t times 1. So natural log 1.6 equals 0.02t. Just divide both sides by 0.02. Those divide out, so we just have t is natural log 1.6 over 0.02, which is approximately 23.5 years. That's how much time would have to pass to have $8,000 on account. Our next example says an account pays 3% annually, compounded continuously. How much time must pass before the original investment doubles? So it doesn't matter what your original investment is. You can call it anything, but the amount on account is twice that. So just call it P. So the amount on account when it doubles would be 2P. Interest rate is 3% annually, 0.03. I want to solve for T to find out how long it takes for that to double. Replacing A with 2P, replacing R with 0.03, we get 2P is P times E to the 0.03T, and we want to solve for T. Dividing both sides by P, and you just get 2 equals E to the 0.03T. We solve for an exponent by taking the natural logarithm of both sides. Natural log of 2 is natural log E to the 0.03T. Pull that exponent down, 0.03T comes down in front. You get natural log 2 is natural log 0.03t times natural log e, but natural log e is just 1. E to the first power is e. So we have log 2 equals 0.03t. All we've got to do is divide both sides by 0.03, and we get about 23.1 years this time. To double, but we had a higher interest rate. That's why the amount of time is about the same, even though the first case didn't double and the second case did. So continuous compound interest is nice. Our formula is A equals PE to the RT. But it's really just one example of exponential growth and decay. So here's the form I prefer. Y equals CE to the KT. K is the growth factor. If k is positive, things are growing, getting larger. If k is negative, they're decaying, they're getting smaller. That's one way for us to keep this in mind. And c happens when t is 0, because if t is 0, we have e to the k times 0, which is e to the 0, which is just 1. So c is your initial amount. C is what you get at time 0. So we're going to need to figure out c, our initial amount, figure out k, our growth constant, to be able to use this model. So here's our example here. A colony of bacteria grows exponentially. Initially there are 1,000 bacteria present. That will be c. After 1 hour, after t equals 1, there are 1,500 present. Find the equation that describes the size of the population and then use it to predict the number present after 4 hours. So let's go through that process. Y equals ce to the kt is what we're trying to use. Initially there are 1,000 present, so at time 0 there are 1,000. So y of 0 is 1,000. At time 1 there are 1,500 present. So y of 1 is 1,500. We're going to use this first bit to get capital C. We're going to use the second bit together with the first bit to get k. Let's see how that works. So again, this is the information we have. If y of t is ce to the kt and y of 0 is 1,000, what does that tell me? Y of 0 is ce to the k times 0, but that's e to the 0, that's just 1. So y of 0 is c times 1. So y of 0 is c and y of 0 is 1,000. Put it both together, what does that tell you? C must equal 1,000. Over on this side, y of 1 is 1,500, and again we're starting with y of t equals ce to the kt, but we know that c is 1,000, so we'll replace that. We also know that when t equals 1, the answer is 1,500. So you have 1,000 for c equals e to the k times 1 equals 1,500. So we're going to divide both sides by 1,000 here, and we're going to get 1.5 equals e to the k. And then to solve for k, we're going to take the natural log of both sides. So natural log of 1.5 equals natural log e to the k. And then we'll pull that k down. So that's k times natural log e. And we get what? We get 0.4055 equals k. So I know c is 1,000. I know k is about 0.4055. If we put those things together, we can answer our question. So there is our formula. And we wanted to know what happens at 4. So recalling the original question, it says, find the equation, we've done that describes the size of the population. Use it to predict the number present after 4 hours. So I need y of 4. Now I know c and I know k. I'm going to plug in a 4 for t, and I'll get the approximate value of the number of bacteria we should have at that time. So there's the formula again. Y of t is 1,000 e to the 0.4055 t. I want to know what y value of 4 is. That'll be 1,000 e to the 0.4055 times 4, which we'll just go ahead and use a calculator to approximate that. And we get approximately 5,063 bacteria should be present 4 hours later. So we had a positive k. Our k was 0.4055. That means it's growing. The number of bacteria is increasing when the growth constant is positive. We'll look at one more example here. A radioactive isotope has a half-life of 20 years. So after 20 years passes, half of the original material decays away. An initial sample has 5 grams of that isotope. How much time must pass before less than 1 gram remains? So we're starting with y of t is ce to the kt. My initial is 5. So if you plug in a t of 0, again you'll see capital C is going to be 5. The half-life of 20 years tells me 20 years out how much is left. Well, if I start with 5, 20 years left will be half of 5, or 2.5. So this is the other bit of information I need. So I get C for my initial, but I've got to get K. I'm going to need to use y of 20 as 2.5 to be able to solve for K. So again, first off, 5 is y of 0, which is ce to the k times 0. E to the 0 is 1. 5 is c. No problem there. Now, the other part tells me y of t is ce to the kt. 2.5 is y of 20. Plug in a 20 for t. So 5 e to the kt, 5 e to the k times 20. So we get 2.5 is 5 times e to the 20k. Divide both sides by 5, and I get a half is e to the 20k. Hitting both sides of the natural logarithm, natural log of a half is natural log e to the 20k. The 20k can come down in front of the natural log e. Natural log of e is just 1. So we divide both sides by 20, and I get k is log a half divided by 20. If which is approximately negative 0.03466. K is negative. It is decaying. The number of grams of the radioactive isotope I have is decreasing over time. Now, the question I asked is how much time must pass before less than 1 gram remains? Well, I know C and I know K. If I call Y 1 and go a little bit beyond that, that'll do it for me. So plugging in C is 5 and K is negative 0.03466. You get Y is C e to the KT, Y is 5 e to the negative 0.03466 t. But I want to find t such that Y of t is 1 and go a little bit beyond that, it would be less than 1. So divide both sides by 5, and then we get 1/5, or 0.2, is e to the negative 0.03466 t. Now hit both sides with a natural logarithm. So natural log 0.2 is natural log e to the negative 0.03466 t. Pull this down in front, that exponent down in front, and we get natural log of 0.2 is approximately negative 1.609. Pulling that exponent down, negative 0.03466 t times natural log of e will equal that, but natural log e is just 1. So all I've got to do is divide both sides by negative 0.03466 to solve for t. And what do we get? We get about 46.4 years before we are at this level, before less than 1 gram remains. And that will conclude this lesson.